So as we're putting more and more force, we're actually going to have initially kind of a quick slight bend to the bone, but then it's going to hold its shape pretty well until right near the end where it's going to start to shift again, and that's where it would snap. So when we're talking about how our bones are and different load curves, so if it's really brittle, it's barely going to move at all until it breaks. A normal bone, we're going to have obviously a little bit more displacement. So you can see it's not really that exponential. Instead, this is that curvilinear type relationship. Yeah, and notice ductile, aka this is a child that happens to have not their growth plates fused yet, so there's a lot of flexibility. They're going to in turn have a lot more ability to bend. Notice this is force increases until it breaks. I highly suggest not ever lifting up anything heavy enough that you start to feel your bones starting to bend. However, like anything else, our tissues can only deal with so much deformation. So does that kind of give you more context of what we're talking about there, Kristen, and kind of what we're really going for? Yeah. Why bones break? Because you put too much freaking force through them. It's science. Actually, I'll throw this up in the chat so you guys can, if you're interested, you can do a little bit more reading on it. But it's actually kind of neat if you think about it. So, yep, notice there's Young's modulus, okay? The slope of the curve, okay? And then the height, that's obviously the greatest strength can deal with. And notice when we hit that yield point, that's where we're transitioning above where now, notice guys, where you're causing permanent damage to the structure. So we're literally talking about potentially warping our bones. Now, the amount of force that you're having to have to go through, this is going to be a whole lot. Plus, let's face it, depending on how this force is being produced. So if we're putting it, straight through the bone and that it's compression, we're going to have this bending at some point. Whereas if we're trying to go effectively in an acute angle aggressively, that's going to be a lot easier of a point to break from. How cool is this? The tympanic bulla, aka the eardrum of the fin whale. That's so cool. Oh man, we got different types of fractures. Man, you're making. Okay, I'm gonna stop because we all know I'll probably spend way too much time looking at this. So let's go ahead and go back to our study exam. So question 1, as we bend forward at the hips, how does the compressive force on the back change? So think increase, decrease, or stay the same. What do you guys think is going on? Exactly, it's going to decrease because now instead of having all that weight stacking up and compressing, we're leaning forward, so we have less compressive strength. And now what type of stress have we increased? What type of force have we increased? Decreasing compressive force, what are we increasing? Absolutely. So the next question is going to be increase. So as you're going to hyperextension in your lumbar spine, okay? What part of the disc, so think anterior, posterior, is experiencing tension? Because think about it, your lumbar are on top of each other. So when we lean back, we're opening on the front, but we're clamping down on the posterior. So the posterior is actually where you're going to be feeling compression. It's going to be the anterior, where you're going to now be feeling tension. Okay, so notice the apex of flight, medicine ball, 3 meters off the ground. It's got load. It's got both potential energy to fall and it's got kinetic energy where it's moving forward. So hence its total energy. Oh gosh, sorry. Is going to be equal to the kinetic energy plus the potential energy. So then we have 0.5 times its speed, which is going to be 10 times 10, because we've got, it's obviously 10 squared, and then multiplied by its mass, which is 10 kilograms. Then we have adding to this separately, which is the mass, 10 kilograms, multiplied by gravity, 9.81, multiplied by 3 meters. Now, this is just breaking down that centripetal force when notice velocity of rotation doubles and the mass decreases by half. So effectively, this is just a where if all these values are 1, okay, well now we take that mass, divide by 2, but your real final equation, if you're thinking about, we're going to have so if we're really going to factor it, what you're going to end up with being is whatever your rotational velocity is going to be, you've got that doubling of its square over 2. So in this mathematical version, you're doubling it, but obviously if you've got a much bigger velocity in the first place, it's going to be much higher. So your total change so how does inertia change when the mass of an object increases? How does inertia change, guys? What's going to happen here? And remember, always feel free to bring up our happy, wonderful equation slide. So how will that change, folks? Absolutely. It's going to increase. And it's going to be increasing effectively. Nice job there, Dakota. So how is pressure going to change whenever we go and decrease the area it's applied by 75%, but at the same force? So when we think back to our pressure formula, which folks notice is simply going to be force divided by the area. So what's our next move? Absolutely, but how much is it going to increase, Dakota? Yes. Kristen, that is correct with 4x. Because if you think of it this way, guys, so we've got our pressure equals our force and our area is 1 initially. Then it changes, so pressure equals 1, to 1 divided by, because now we only have 25%, 0.25. So 1 divided by 0.25 gives us 4. Okay. Center of gravity change in an athlete when they get set in a 2-point stance from standing straight up. Where is that center of gravity moving? So think about it's going from standing to now we're crouching down. So it's going to be mostly just inferior. Anterior would mean we're moving forward. So that would be like if you take a lunge or you take a step, like where's your center of mass moving? So next question is, well, I guess I already put the solution here, so it's pretty easy, but remember the, excuse me, inertia of a limb is going to be equal to its mass times its radius squared. So we go from 10 times 1 squared equals 10 to 10 times 0.5. So notice it changed squared. So that gives us now all of 2.5. So this would be overall, it decreases by 4x. So now, how does our torque change if you double the length of the lever arm? Absolutely. Good job, Marlano. So, following up, how fast would we have to jump off the ground in order to jump at least 2 meters in the air? So what do we need to do to solve for this one, guys? How do we set this up? You can, if you want to do it the nightmare hard version. I would suggest not. There's a simpler way to do it. So what do we need to do to solve for this one, guys? No, you actually don't need to find the force coming off the ground. That would be something very useful, Josh, because then we have their initial acceleration off the ground. But that's something we don't have. Gravity is definitely a component of it, for sure, Dakota. Not so much because, once again, we don't have time yet. So it's not going to give us the ability to figure that out. Think about how we're going to be converting from two different types of energy. That's how you figure this out quickly. We're converting from two different types of energy. Absolutely. We're converting from potential energy to kinetic energy. So we know our kinetic energy, whenever we leave the ground, is going to be equal to our potential energy at the top of our jump. Okay? So that means 1/2 of the mass times the velocity squared. And the bottom is going to be equal to the mass times gravity times height of the top. Okay? So now we start factoring. Which of the units, so think letters, can we just get rid of immediately? Because we've got M, because we have them on both sides. So give it away. Bingo. So now we factor to 1/2 of the velocity squared equals gravity times height, because they're going to be the same mass when you're going to be the same mass when you jump off the ground as when you're at the top of the jump when you come back down, unless you're like vomiting while jumping or something else, and that sounds really unpleasant. So we're not doing that. Okay. Well, now we still have no idea what our velocity is, but we do know what's gravity. Bingo, 9.81. And then what's that height? Great job, Dakota. So then, okay, we now have 1/2 of the velocity squared equals, whoa, buttons aren't toys, Mike, buttons aren't toys, equals a grand total of 19.62. So now what are we going to do? What's our next step factoring? Absolutely, Kristen. So we would be left with V equals the square root of, because now we've taken that 19.62 and multiplied it by 2 before we took that square root. So that would give us 39.24. And there's your velocity. Which is going to be what? 6.3, 6.4? What do you guys come up with? Awesome. Okay, now we're going to go ahead and we could go and figure out that flight time if we wanted to. That's where we're going to go ahead and take our vertical distance formula, where we have our initial velocity, we've got our acceleration, gravity, and then we're just going to say we start on the ground and we end on the ground. So it'll be the total flight time. So then we would take that total flight time, take half of it, and that should give us the actual distance height. But then, oh, sorry, not only do we have to do the vertical distance, but then we'd have to do the quadratic formula. Does that make sense to you guys? Nice. How do you set up your basic hard version of it? Did you go through and try to solve through your distance and otherwise?
I did, yeah. I solved it for like my fall back to the ground, and then I found the one-way time. And then once I had that, it was yeah, then I recognized that initial velocity and final velocity should be the same. So eventually I got there, but it was the exact same answer, and it was much faster this way.
Yeah, no, that's what I was like to say. There's the easy way and the hard way. So yeah, you did the hard way, but you did a good job of thinking your way through it. which is, you're starting at 2 meters, then you got to follow the ground. So yeah, you do the vertical distance formula, only, yeah, your initial velocity is 0, your acceleration is going to be gravity, and then your y coordinate is effectively going to be 2. And yeah, how long does it take you to just boom, hit the floor from that period of time? And then yes, you figure out the inverse of that for the velocity, and the numbers, notice, you end up with the same, which is, it's wild, but it's a kind of a neat thing for you guys to work your way through doing it the hard way. So take just essentially the math of falling from 2 meters, solve for the time, and then double the time and solve for the initial velocity. Now that works. And it's neat because it shows you guys we can convert from this one number to another number to another number. So like anything else, like, yes, we have these values, but these values have meaning. Like, these are actual, like, quantifiable things we're going to see in reality. So like, for example, okay, when we talk about power, okay, what is the unit for power, guys? What's the unit for power? Good, watts. Okay. Where do you guys see the term watts utilized all the time? Light bulbs. Okay, exactly. So if it says it's a 60-watt light bulb, that's how much power needs to be running through it consistently in order for it to be lit up. That's it. So the watts that we're producing whenever we jump, when we run, when we throw, well, that's power that we are producing with our body doing mechanical work. And so hence why you can be, I'm sure you guys have seen those little hand crank generators for flashlights, or the sometimes people have like their bike hooked up to a little generator that'll power something small. Well, that's using the wattage that you're producing to run another object. And so, like anything else, we're just converting from one type of power utilization to another type of power utilization. And it's just kind of fun because then you can kind of work your way through, like, okay, how much energy does it take to light a light bulb? Okay, how much energy does it take to light a bunch of light bulbs? And could you actually keep all those light bulbs lit by just riding on a bicycle, that all of the work that you're producing is being harnessed to do that? And then for extra fun facts, not that I think any of you guys wanted this, but work, that's what kilojoules is going to be, or joules is going to be the units for that. And that's actually what you can convert calories into, as in the food you eat, into work. So hence, you'll sometimes see, if you're in European countries, where their nutrition facts will be actually in kilojoules, because that's literally how much work you can perform thanks to eating that food. So the more you know. All right. So we got a ball that somehow has a coefficient of restitution of 1.4, meaning it somehow manages to bounce a little bit higher after every single time it hits the ground, which makes no mathematical sense. How high is it going to go after its second bounce? Great job, Lexi. Because we're going to take 10 times 1.4 and then multiply that by 1.4, which I'm going to say Lexi's right. So I definitely can tell you, after the first bounce, we're just going to take 10 times 1.4, so we're going to be equal to 14 meters. So then when we go ahead and multiply that by 1.4 again, rock and roll. Good job. All right. So in this problem here, guys, which of the two frictions are we going to utilize as far as trying to figure out what we need to move the block? We're going to use the static or the dynamic friction. Notice it's to move the block, not to keep the block moving. What type of friction do you think we're using? Bingo, bingo. So we're going to take that 0.9 and multiply that by 8,000, and that's going to give us the force we need in order to move that block. And now we're going to get ourselves to another happy leverage formula, okay? So remember, we're going to have effort times effort arm equals resistance times resistance arm. So who wants to go and set this up in the chat of how we would start to go about this? Awesome work. Now, remember, we're forgetting one thing. So you've got the basic setup correctly, but are we going to use kilograms or bingo? We have to deal with the reality of gravity pulling it down. So that was about perfect, Marlana. We just need to still incorporate gravity.
May I ask a question?
Go for it.
So if you're trying to apply force to like a bolt on the ground or whatever, is there still gravity to take into account because you're only moving the wrench horizontally? Does that make sense? I was thinking it's like it's an effort and resistance arm problem, but you're just not lifting it up.
Okay, so you're thinking it's like this.
Yeah.
As opposed to like this.
Right. Right.
Awesome. Okay, so the question is, if it's like this, then think about it. Where we'd either actively have to be pushing this way, so we would still not really use kilograms. We would use newtons as force. So we'd want to, I'd probably give you better units. Instead, the assumptions we're working with here, if I'm just giving you the weight, then gravity is what's pulling it down.
Okay.
Now, you're right. We could have this situation where you're right. We just have the newtons pushing this way and then the newtons pushing this way, which, I mean, like that is going to be a legitimate situation you could potentially encounter. And then for, yeah, the total force the lever arm is producing, I didn't do a good job of giving you that basic, like the arm is held, parallel to the ground.
Okay.
So that would be the assumption that I put in there, but that's a good job questioning the assumptions and asking why we're approaching things the way we do.
This is one related question to that. When we have, if we hear something like it's a 30-degree angle to the floor, is that like an acute angle to the floor, or is it like it's already parallel to the floor and then it goes up 30 degrees from there? Does that like to the horizon, like 30 degrees there, or is it 30 degrees to the floor, like pointed down?
That is a great question. I need to do a better job of writing them. Yeah, so we're thinking about like the floor is 0, 30 degrees.
Okay. Perfect. That's what I thought, but my whole family disagreed with me. So
No. That is poor question asking, and I will wear it. So when you think about, if I should say 30 degrees above parallel to the floor, does that make sense?
that makes sense.
Or 30 degrees below parallel to the floor. So like, the floor is 0. So hence, like if I say your arm's straight out to your side, well, and if I say if your arm's hanging straight down, most people should be able to assume that it's probably just straight down, straight out, and like you're holding like your body in a big letter T. Okay. Hopefully you can infer that one, but that's a good question. Thank you for holding me accountable.
Thank you for explaining it.
No worries. So then getting back to the question we're at right now, 0.75 times 20 times 9.81. And we are going to take all of that and divide it by 0.03. And that's going to equal our resistance. Because remember, 0.03 is the resistance arm, Marlana, but that's me catching my own little kerfuffle. Awesome. Jordan, you got a question? Jordan does not have a question. All right. So we now have ourselves a power question. So how much power do you produce if you lifted 200 kilograms upwards 2 meters in 0.5 seconds? So what do we need to do here? Remember, guys, power equals work over time. Okay, notice it's over time, not multiplied by time. It's divided by time. Okay. And then work equals our force times our distance. Okay. And then just because we need to do one more step, the way I set this up, force equals your mass times your acceleration. So we've got 200 kilograms. What do we need to multiply it by to get it into a force? Bingo. Now we've converted that. So when we multiply those two together, we'll have the force. What do we now have to multiply this by in order to get our distance? Or get it into work. We need to multiply by the distance. And what was our distance? Bingo. And so then, in order so we can, so this will altogether equal our work. So now what do we have to do to get this converted into time? Oh my gosh, converting the power. What do we have to do? What do we have to do? Bingo, divide by time. Quite possibly, Dakota. I have not multiplied all that together. But that looks correct. So then we're going to take the 200 times 9.81 times 2, close, divide by 0.5 equals your power, which in turn is going to equal your wattage, which in this example should be 7848. Great job, guys. Great job. All right. So then we've got an object. It's traveling at 15 meters per second and deaccelerating 2 meters per second. How far will it have gone in 5 seconds? So hence, we're going to have that distance equals our initial velocity plus the 1/2 of, oh geez. And this should be plus or minus, my God. Plus or minus 1/2 of his acceleration times time squared. Okay. So x is going to be equal to 15 times 5. So we've got those meters per second, and then that's 5 seconds. Now, is this going to be a plus or a minus sign here? It's going to be a plus or a minus sign. Bingo, because we are going to be going slower. So it'll be minus 1/2 times 2, because that's that deacceleration, meters per second squared, times 5 squared. Okay. So then we'll run our maths on each of these. So we've got 75 minus, okay, 5 squared is 25, times 2 is 50, divided by 2 is back to 25. Make sense, everybody? Here should be an easy one, guys. If acceleration of gravity doubles, how much would your body mass change? Bingo, stays the same. Now, if it was gravity doubles, how much does your body weight change? Okay, now your weight's going to double because the factor of gravity is increased that much. Great job. Okay, if your arm is 20% closer than the point of insertion, which is 0.12 meters from the axis, the resistance is 10 kilograms with a resistance arm of 0.45. How much force needs to be produced? So we have the basic setup of notice 10 times 9.81 times 0.45 equals our force times 0.12. And notice, since it's 20% closer, it's going to be at 80% of that initial length. Does that make sense? So it's not we multiply that by 0.2, because that would say it's at 20% of its initial length. So instead, that's why I multiply by 0.8. And then we would factor accordingly on through. Folks, forgive me. Nature is beckoning. I will be back briefly. But I want you guys to work on solving these problems right here. And by solving here, think about what's going to be the organization for first class, second class, and then third class, along with the different parts of the spinal cord. Yes, you could do that, Marlana. You could take 0.12 times 0.2, take that number and subtract it from 0.12. That gives you 80% the same way. Absolutely. So work on trying to solve for each of these. And then we'll go through them whenever we get back, think. Ooh, spelled it right the first time. Be right back, guys. So, Kristen, from the quiz, what you're looking for there is going to be its lordosis in the lumbar spine. Think about excessive curvature, like kind of big belly. It protrudes from either a really high amount of adipose on the abdomen or from pregnancy. So most like women in their third trimester are pretty much always going to have lordosis. And that's the excessive lumbar curvature. That's why a lot of pregnant women complain about their back hurts. Makes perfect sense. You've got a lot of weight pulling you forward in that position. Kyphosis is the excessive hunching in typically the thoracic spine. And then you've got scoliosis, where you just kind of have that S curve in general. And that's just, something unfortunately can happen, but it's something definitely to be, careful of. It's more of a developmental thing, but if it goes too far, you can have some issues with nerve pain and back pain. So, how many of these questions were you guys able to solve? All of them, right? Yes, Jordan? Fair enough. So that's going to be a lordic curve. It's curving backwards. So there's a, so that's not necessarily a pathology. That's just a natural curvature you're going to find. Now, what you can have is people that get that excessively forward lean because of bad posture. Oh, it just doesn't feel good to even play around with. Just due to, bad posture for incredibly long periods of time. And that's going to be related to potentially some issues with even things like breathing. Okay, so remember, no worries. Our first class levers are always going to be where the axis is in the middle. Okay, where our second class lever, and remember that's pretty much what our entire body is going to be, is our resistance, our force is going to be in the middle. And then finally, our third class, our good old wheelbarrow that we don't get to utilize too frequently, is going to be where we have our force, resistance, and then our axis. Sorry, I'm messing that up. Second class is wheelbarrow. Third class is going to be our typical movement. Somebody didn't get enough sleep last night. Do you guys have any other questions? I guess obviously you guys weren't able to make much headway on the questions you could see on the screen while I was gone. You kind of, how to say, at a point today where you guys want to break, or you guys want to keep going? Obviously, we've got a gold star attendance day, aka there's only 10 of you. You know what? Showing up is one of the easiest things to do, but yet is somewhat quite difficult. So give me one moment. Resume the share. So the nice thing, arbitrary things because you feel like it. And the nice thing is I stopped recording whenever I just did that. So the ones that didn't make it today will never even know that this happened, except for I recorded that part. So now they're asking what happened. Exciting, isn't it? Are there any other questions you guys want to review on today? Honestly, I'd say sit down with the rest of this, and you can see the name of the document at the top of, going through the study guide, and then feel free to come and bring questions. And then we'll probably have another, one or two more difficult kind of for fun questions. And if we have better attendance, we'll try to actually get you guys doing more of your project working in your groups for Thursday. But if there's no other questions, you guys okay with getting out about 4 minutes early? Or do you guys prefer for me to just kind of keep talking? Yes, Dakota, we will definitely be reviewing. So right now, while I'm in Blackboard on the other screen, that's why I hit pause, because I don't want to bring up everybody's grades, because that's a real jerk thing to do. But currently, your exam 2 is all slated to where you have to take it by the 23rd. So it is next week when it's going to be due. But yeah, so we're going to be just reviewing also on Thursday for your exam, and then you'll take the exam next week. And then we've got, obviously, we're going through the lower body and more topics, and then you guys are going to be free of me. And yeah. Any other questions, comments, concerns? Anytime, Dakota.
Can I return to the strain problem from the homework, or should we not go? Do you not want to touch that?
If you want to go back to it, we can keep doing strain stuff. It's okay.
Okay, I feel like the part that I'm getting hung up on is 40 newtons divided by length constant. Is there a length constant, or what does that mean? Do we hold the length constant?
So when we're going with a linear relationship or a logarithmic, so I think this
It's been a while, so maybe it's
no,
not really.
It's okay. It's okay. So
okay,
let me see if I can do. Okay. So if we're saying it's a linear relationship, okay, that means it's going to look like this. As the one goes up, the other goes up. Make sense? So if it's 500 newtons per 5%, so then effectively as we're going to go through and go from 5% to 10% to 15 to 20 to 25, et cetera, it's going to always have that perfect stack. So it's going to go from 500 newtons to 1,000 to 1,500, so on and so forth. Make sense?
Yes.
Okay. So the other one that we're looking at is more of an exponential. So think of it like a parabola. Okay. So what we're looking at is more of a doubling.
Like COVID.
What's that?
Like COVID.
Oh yeah, the joys, yeah, like diseases. You're right, absolutely. COVID being the one that's the most prevalent in our minds, but yeah, there's obviously a lot of other diseases that can multiply pretty rapidly. And then I also have my own questions about human stupidity, but that's not part of this class. That's more of an existential fear that I have. Okay, so if we figure it's going to go from being, and this is just because I drew my graph so wide, the first mark would be here, but then the second mark would be here, and then the third mark would be here. So notice it's kind of doubled between each of these. So it's going to go from 500 to 1,000 to 2,000 to then it would be off this chart because it'd be at 4,000. So that question so much isn't about true physics, because notice we went through and looked at those deformation curves with bone, where you see it's more shaped like this, and then Snap City. Instead, it was more of, okay, if it's a linear relationship, then we should be able to figure out where it's going to be on the line. If it's an exponential, logarithmic, then we should see that type of doubling. So it's more of a thought exercise than a true like mathematical definition.
Okay.
But if we were to work with springs are going to be a little bit more curvilinear than just straight up linear. And we've gone over. So stay safe out there, guys. Thank you guys for showing up today. Come with questions and we'll keep working our way through the review. And then anything else you guys want to go ahead and just go through in general so you guys feel ready for that exam. Take care of yourselves, and I will see you guys on Thursday morning. So, bye-bye.